The universe is stranger than we imagine, and the most terrifying things in space are not the monsters of science fiction or the aliens we dream about meeting someday. No, the real terrors are far worse. They are silent, they are invisible, and some of them could end all life on Earth without any warning at all. Tonight, we journey into the darkness between the stars. We travel to places where light itself becomes a prisoner. We explore regions of space where the very fabric of reality could tear apart at any moment. This is a story about the cosmos we call home, a universe so vast and so strange that our tiny human minds can barely begin to understand what we are looking at. And the deeper we look, the more frightening it all becomes. Space seems peaceful when you look up at the night sky. The stars twinkle gently, the moon glows soft and white. Everything appears calm and beautiful from where we stand on the surface of our small blue planet. But that peace is an illusion. Behind that curtain of darkness lies a universe filled with violence, destruction, and mysteries that could swallow entire galaxies without leaving a trace. The cosmos is not our friend. It does not care about us. It does not even know we exist. And the forces that shape it are so powerful that they make everything humans have ever built look like sandcastles waiting for the tide. Let us begin our journey at the edge of a black hole. These cosmic monsters are perhaps the most famous terrors in all of space, and for good reason. A black hole is what happens when gravity wins. When a massive star runs out of fuel at the end of its life, it can no longer push outward against the crushing weight of its own matter. Everything collapses inward in an instant. The core of that dying star gets squeezed down into a point smaller than the period at the end of this sentence. And yet, all that mass is still there. All that gravity is still pulling. The result is a region of space where gravity is so strong that nothing can escape. Not matter, not radiation, not even light itself. The boundary around a black hole is called the event horizon. This is the point of no return. Once something crosses that invisible line, it is gone forever. There is no coming back, no rescue mission, no second chances. The event horizon is not a physical surface you could touch. It is simply the place where the speed you would need to escape becomes faster than light can travel. And since nothing can move faster than light, anything that crosses that line is trapped for eternity. What happens to objects that fall into a black hole? This is where things get truly disturbing. As you approach the event horizon, gravity pulls harder on the parts of your body that are closer to the center. If you fell in feet first, your feet would experience stronger gravity than your head. This difference stretches you like taffy. Scientists call this process spaghettification, and the name is accurate. Your body would be pulled into a long, thin strand of matter. Every bone would snap, every muscle would tear, every atom in your body would be ripped from its neighbors as you are stretched thinner and thinner. But here is something even stranger. Because of how gravity bends time, someone watching you fall from a safe distance would never see you cross the event horizon. Time slows down as you approach that boundary. To an outside observer, you would appear to freeze in place, getting redder and dimmer as light struggles to escape the growing pull. You would seem to hang there forever on the edge of oblivion. But from your own perspective, you would cross the horizon in an instant and be destroyed shortly after. This is what happens when space and time become twisted beyond recognition. Black holes are not rare. Our own galaxy, the Milky Way, contains millions of them. Most are stellar black holes formed from collapsed stars, with masses between 5 and 50 times that of our Sun. But at the center of nearly every galaxy sits something far more terrifying. Supermassive black holes have masses millions or even billions of times greater than our Sun. The one at the heart of the Milky Way is called Sagittarius, a star. It contains about 4 million solar masses squeezed into a region smaller than our solar system, and it is relatively quiet compared to others. Some supermassive black holes are actively feeding. They are surrounded by swirling disks of gas and dust that spiral inward like water going down a drain. This material gets heated to millions of degrees as it falls, releasing enormous amounts of energy. These feeding black holes are called quasars, and they are among the brightest objects in the entire universe. A single quasar can outshine all the stars in its host galaxy combined. They are beacons visible across billions of light years, and at the center of each one sits a monster devouring everything that strays too close. But even the largest black holes are not the only cosmic killers we need to worry about. Far from it. Let us now turn our attention to something that travels at the speed of light and carries more destructive power than we can comprehend. These are gamma-ray bursts, and they represent one of the most violent events in all of nature. Gamma-ray bursts were first detected by accident in the late 1960s. American military satellites designed to watch for secret nuclear weapons tests kept picking up mysterious flashes of gamma radiation coming from space. At first, scientists thought these might be signals from alien civilizations. The truth turned out to be even more dramatic. These bursts were coming from distant galaxies, and the amount of energy they released was almost impossible to believe. In just a few seconds, a single gamma-ray burst can release more energy than our sun will produce over its entire 10 billion year lifetime. There are two main types of gamma-ray bursts. Long-duration bursts last more than 2 seconds and can go on for several minutes. These happen when massive stars at least 40 times heavier than our sun reach the end of their lives. The core collapses to form a black hole, but the outer layers do not fall straight in. Instead, they swirl around the newborn black hole and create jets of material that shoot outward at nearly the speed of light. When these jets punch through the surface of the dying star, they release a focused beam of gamma radiation that can travel across the universe. Short-duration bursts last less than 2 seconds. These occur when two neutron stars spiral toward each other and finally merge. Neutron stars are the compressed cores of dead stars, so dense that a teaspoon of their material would weigh billions of tons on Earth. When two of them collide, the resulting explosion creates a brief but incredibly powerful burst of gamma rays. These mergers also forge heavy elements like gold and platinum, scattering them across space to eventually become part of new planets like Earth. What makes gamma-ray bursts so terrifying is what would happen if one occurred nearby. The beams are narrow, like the light from a laser pointer, so the odds of Earth being in the path of a distant burst are small. But small is not zero. If a gamma-ray burst happened within a few thousand light years of our planet, and the beam was pointed directly at us, the results would be catastrophic. The high-energy radiation would strip away our ozone layer in seconds. Without that protective shield, the surface of Earth would be bathed in deadly ultraviolet light from our own sun. Plant life would die, the food chain would collapse, most complex life forms would go extinct within months. Some scientists believe that a nearby gamma-ray burst may have caused one of the great mass extinctions in Earth's history. About 450 million years ago, during what is called the Ordovician extinction, life on our planet experienced a devastating die-off. Up to 85% of all marine species vanished in a relatively short time. While the exact cause remains uncertain, a gamma-ray burst hitting Earth from a dying star within our arm of the Milky Way is one leading theory. If this idea is correct, it means our planet has already survived one of these cosmic assassinations. Whether we would be so lucky a second time is anyone's guess. The scary part is that we would have no warning. Gamma rays travel at the speed of light. By the time we detected an approaching burst, it would already be here. There would be no time to prepare, no time to evacuate, no time to say goodbye. One moment, everything would be normal. The next moment, our atmosphere would be on fire. This is the reality of life in a violent universe. Death can come from the stars without any notice at all. But gamma-ray bursts are not the only threat that moves at the speed of light. There's something else out there, something so strange that even physicists struggle to fully understand it. This concept is called vacuum decay, and it might be the most terrifying idea in all of science. To understand vacuum decay, we first need to talk about what nothing really means. When we think of empty space, we imagine a perfect void with nothing in it. But that is not how the universe works. Even in the emptiest regions of space, there is something called the vacuum energy, a kind of background hum built into the fabric of reality itself. This energy determines the fundamental laws of physics, the strength of forces, the masses of particles, everything that makes our universe work the way it does. Here is the problem. Scientists are not completely sure that our universe is in its most stable energy state. It might be that we are living in what is called a false vacuum. Think of it like a ball sitting in a small dip on the side of a hill. The ball looks stable. It is not rolling anywhere. But there is a much deeper valley at the bottom of the hill. If something gave that ball a little push, it would roll down and never come back up. Our universe might be like that ball. We might be stable for now, but there could be a lower, more stable state waiting below. If our universe is in a false vacuum, then at any moment, anywhere in space, a random quantum fluctuation could push a tiny region into the true vacuum state. What would happen next defies imagination. A bubble of true vacuum would form and begin expanding outward at the speed of light. Inside this bubble, the laws of physics would be completely different. The atoms that make up your body would not work anymore. Chemistry as we know it would cease to exist. Stars could not burn, planets could not form. Everything familiar would simply stop being possible. The bubble would consume everything in its path. Galaxies would be erased. Trillions of stars would vanish. And we would never see it coming because it moves at exactly the same speed as the light that could warn us. One moment you would be reading these words or thinking about what to have for dinner. The next moment you would not exist. There would be no pain, no awareness, no time to even know what happened. You and everyone you have ever loved and everything humanity has ever built would be gone in an instant that you would never experience. Is this going to happen? Probably not anytime soon. The current scientific understanding suggests that even if our universe is in a false vacuum, it is metastable, meaning it would take an incredibly long time for vacuum decay to occur naturally. We are talking about timescales that make the current age of the universe look like the blink of an eye. But the unsettling truth is that we cannot rule it out completely. Somewhere, perhaps in a distant galaxy right now, a bubble of true vacuum might already be expanding, times once others. It might have started billions of years ago. It might reach Earth tomorrow, or it might never come at all. We simply do not know. This uncertainty is part of what makes the universe so frightening. We are used to being able to see danger coming. We watch for storms on the horizon. We look both ways before crossing the street. But the cosmos does not work that way. Some threats are invisible until the moment they end everything. Let us shift our focus now to something slightly less catastrophic but equally mysterious. We have talked about black holes, those regions where gravity traps even light. But there is another substance filling the universe that we cannot see, cannot touch, and barely understand. This invisible material is called dark matter, and it makes up about 27% of everything that exists. Dark matter does not glow. It does not reflect light. It does not interact with ordinary matter in any way except through gravity. We know it exists only because we can see its effects on things we can observe. Galaxies spin faster than they should based on the visible matter they contain. Without dark matter holding them together, they would fly apart. Galaxy clusters bend light from distant objects more than the visible mass can explain. The cosmic web of structure we see across the universe could not have formed without dark matter providing a gravitational scaffold. What is dark matter made of? Despite decades of searching, we still do not know. It is not ordinary atoms. It is not made of protons and neutrons and electrons like the stuff that makes up you and me, and every star in the sky. It must be some exotic particle that we have never detected directly. Underground laboratories have been running experiments for years, trying to catch a dark matter particle interacting with normal matter. So far, nothing. The ghost that holds our galaxy together remains completely invisible. Even more mysterious than dark matter is dark energy. This strange force makes up about 68% of the universe, far more than matter of any kind. Dark energy is what is pushing the expansion of the universe to accelerate. Every day, the space between distant galaxies grows a little larger, and this expansion is getting faster over time. When the universe began in the Big Bang nearly 14 billion years ago, everything was squeezed together in a hot, dense state. As space expanded, things cooled down. Galaxies formed, stars ignited, planets coalesced. For most of cosmic history, the expansion of the universe was slowing down because gravity was pulling everything back together. But about 5 billion years ago, something changed. The expansion started speeding up. Dark energy, whatever it is, overcame gravity and began pushing the cosmos apart faster and faster. The consequences of this acceleration are profound and disturbing. As the universe continues to expand, distant galaxies are moving away from us faster than the speed of light. This does not violate the rules of physics because nothing is actually traveling through space that fast. Instead, the space itself between us and those galaxies is growing. This means that light from those galaxies will never reach us. They are beyond our cosmic horizon, lost to us forever. In the far future, perhaps 100 billion years from now, the sky will look very different. All the galaxies outside our local group will have receded beyond the observable horizon. Astronomers of that distant era, assuming any exist, will see only darkness when they look up. They will have no way of knowing that the universe once contained hundreds of billions of galaxies. All evidence of that grand cosmic structure will have vanished beyond the edge of their visible universe. Imagine living on a planet where the night sky is completely black, except for a handful of local stars. Imagine having no way to discover the true size and nature of the cosmos. This is the future that dark energy is creating. Some physicists worry about even more extreme scenarios. If dark energy increases over time, a process called the Big Rip could tear the universe apart. First, galaxy clusters would be pulled away from each other. Then, individual galaxies would disperse. Stars would drift apart from their neighbors. Eventually, even planets would be ripped from their orbits. Atoms would be torn asunder. The fabric of space-time itself would shred into nothingness. Everything would end not with a whimper, but with a cosmic explosion of expansion. We do not know if the Big Rip will happen. The nature of dark energy remains one of the biggest mysteries in science. But the fact that this invisible force dominates the universe and that we have no idea what it actually is should give us pause. We are surrounded by something we cannot see, cannot explain, and cannot predict. And this something controls the ultimate fate of everything that exists. Now let us talk about wanderers. Not all worlds orbit stars the way Earth orbits the sun. Scattered throughout the darkness of interstellar space are billions, perhaps trillions of rogue planets. These are worlds that have no star to call home. They drift alone through the void, carrying whatever atmospheres and oceans they might possess into the frozen emptiness between the stars. How do rogue planets form? Some were born around stars but got ejected by gravitational interactions with larger planets or passing stars. Others may have formed directly from collapsing clouds of gas and dust, never having a parent star in the first place. Either way, they are out there, wandering silently through a galaxy that barely notices their existence. Most rogue planets are frozen solid. Without a star to warm them, any surface water would ice over quickly. Their atmospheres would condense and fall as snow. Any life that might have existed would face impossibly harsh conditions. But not all rogue planets are necessarily dead. Some might retain internal heat from radioactive decay or leftover warmth from their formation. Moons of gas giant rogues could have subsurface oceans kept liquid by tidal forces, just like the moons of Jupiter and Saturn in our own solar system. Life might exist on some of these wandering worlds, evolving in total darkness, completely unaware of the stars that fill the universe. The terrifying thing about rogue planets is that we cannot see them easily. They produce no light of their own. They are cold and dark and small compared to the vast distances between stars. One could be heading toward our solar system right now, and we might not detect it until it was very close. If a large rogue planet passed through our system, even without hitting anything directly, its gravity could wreak havoc on planetary orbits. It could fling Earth into a different path around the sun, either closer where we would fry or farther where we would freeze. It could destabilize the asteroid belt, sending rocks careening toward the inner planets. It could disrupt the orbits of other worlds in ways that would cascade through the solar system for millions of years. The odds of this happening are extremely small. Space is vast, and even trillions of rogue planets spread across a galaxy means they are still very far apart from each other. But small odds are not zero odds, and in a universe where we have existed for only a tiny fraction of cosmic time, rare events eventually happen if you wait long enough. Speaking of massive gravitational influences, there is something lurking in the depths of space that has been pulling on everything in our cosmic neighborhood for billions of years. Scientists call it the Great Attractor, and it represents one of the most puzzling mysteries in all of astronomy. The Great Attractor is not a single object. It is a region of space about 250 million light-years away from Earth, located in the direction of the Centaurus and Hydra constellations. Something in that region is pulling our entire galaxy, along with hundreds of thousands of other galaxies, toward it at incredible speed. The Milky Way is currently racing toward the Great Attractor at roughly 600 kilometers per second, or more than 2 million kilometers per hour. At that speed, you could travel from Earth to the Moon in just a few minutes. What makes the Great Attractor so mysterious is that we cannot see it clearly. It sits behind what astronomers call the zone of avoidance, a region of the sky where the disk of our own galaxy blocks our view with dust, gas, and countless stars. Looking in that direction is like trying to see through a thick fog. We know something massive is there because of its gravitational influence, but our telescopes cannot give us a clear picture. Recent observations suggest that the Great Attractor is part of an even larger structure called the Laniakea supercluster. This is the cosmic address of our galaxy. The Milky Way is part of a local group of galaxies, which is part of the Virgo cluster, which is part of Laniakea, and all of Laniakea, containing over 100,000 galaxies, is flowing toward the Great Attractor like water flowing downhill. But even the Great Attractor might not be the final destination. There are hints of even larger structures beyond it, pulling on everything we can see. The scale here is almost impossible to comprehend. We are talking about gravitational influences that extend across hundreds of millions of light years, affecting the motion of hundreds of thousands of galaxies. Our entire cosmic neighborhood is in motion, drawn by invisible forces toward destinations we can barely detect. And there is nothing we can do about it. Earth, the Sun, the Milky Way, everything we know is being pulled along by gravitational currents that span distances far beyond human understanding. Let us now consider the fate of the universe itself. We have talked about individual cosmic threats, like black holes, gamma-ray bursts, and rogue planets. But what happens when you zoom out to look at the entire cosmos? What is the ultimate destiny of everything that exists? One of the most widely accepted theories about the far future of the universe is called heat death. This is not a dramatic ending filled with explosions or cosmic violence. It is something far more quiet and perhaps more terrifying in its own way. Heat death is the slow, inevitable cooling and darkening of everything. The universe runs on energy. Stars burn hydrogen into helium, releasing light and warmth. Planets orbit, galaxies spin. Life grows and thinks and moves. All of this activity requires energy flowing from hot places to cold places. But there is only so much energy to go around, and the laws of physics dictate that over time, energy spreads out and becomes less useful. This is called entropy, and it always increases. In the far future, all the stars will burn out. The fuel that powers them, the hydrogen that has existed since the beginning of the universe, will eventually be used up. Stars will die one by one, leaving behind white dwarfs, neutron stars, and black holes. The galaxies will grow dark. The cosmos will become a cold, lightless void populated only by the remnants of stellar death. Even those remnants will not last forever. White dwarfs will slowly cool over trillions of years until they become black dwarfs, cold spheres of carbon and oxygen that emit no light at all. Neutron stars will fade. And even black holes, those eternal prisons of gravity, will evaporate. This last point deserves explanation. Black holes are not truly eternal. Through a process called Hawking radiation, named after physicist Stephen Hawking, black holes slowly lose mass over incredibly long timescales. The details involve quantum mechanics near the event horizon, but the basic idea is that black holes leak energy bit by bit. A stellar mass black hole would take far longer than the current age of the universe to evaporate, something like 10 to the 67th power years. A supermassive black hole would last even longer, perhaps 10 to the 100th power years. But eventually, they all disappear. What is left after the black holes are gone? Nothing but scattered particles drifting through an ever-expanding void. The temperature of the universe will approach absolute zero. No structures will exist. No energy gradients will remain to power any kind of activity. The cosmos will have reached maximum entropy, a state of perfect disorder from which nothing interesting can ever emerge again. This is heat death, not a bang but a fade, not a catastrophe but a slow surrender to the laws of thermodynamics. Everything that has ever existed, every star that has ever shone, every creature that has ever lived, every thought that has ever been thought, will eventually be forgotten in a universe too cold and empty to remember anything. How long until heat death? The timescales involved are staggering. We are talking about years measured in numbers so large that writing them down would fill pages. 10 to the 100th power years is a 1 followed by 100 zeros. Our universe is only about 14 billion years old, which is roughly 10 to the 10th power years. We are in the very earliest moments of cosmic history. The universe has barely begun. But all beginnings eventually lead to endings, and the ending of everything is heat death. Some scientists have proposed ways that intelligent beings might survive in a dying universe. Perhaps advanced civilizations could cluster around the last black holes, harvesting their energy for as long as possible. Perhaps they could engineer new forms of existence that require less energy. Perhaps they could hibernate for vast stretches of time, waking only when conditions allow brief moments of activity. These ideas are speculation, of course. We have no way of knowing if any intelligence will survive long enough to face the final darkness. But the fact that physicists seriously consider such scenarios tells us something about the inevitability of heat death. Now let us turn to something that moves even faster than we might expect. Hypervelocity stars are stellar speedsters, racing through the galaxy at velocities that defy ordinary stellar motion. While most stars in the Milky Way orbit the galactic center at relatively sedate speeds, measured in hundreds of kilometers per second, hypervelocity stars are moving at thousands of kilometers per second. They are fast enough to escape the galaxy entirely, flying off into intergalactic space, never to return. How do stars achieve such incredible speeds? The most common explanation involves the supermassive black hole at the center of our galaxy. When a binary star system, two stars orbiting each other, passes too close to this black hole, the gravitational forces can tear the pair apart. One star falls toward the black hole while the other is flung outward at tremendous speed. This gravitational slingshot effect can accelerate a star to velocities well above the galactic escape speed. Imagine for a moment what it would be like to live on a planet orbiting a hypervelocity star. You would watch as the familiar constellations slowly changed and distorted. The galaxy that birthed your world would shrink behind you, becoming smaller and fainter, until it was just another smudge of light among billions of distant galaxies. You would be traveling into the void between galaxies, a region so empty that the nearest other star might be millions of light years away. You would be alone in a way that defies comprehension. Hypervelocity stars are rare, but they teach us something important about the dynamics of galaxies. The supermassive black holes at galactic centers are not just sitting there quietly. They are active participants in the cosmic dance, flinging stars into the void, consuming gas and dust, shaping the evolution of their host galaxies over billions of years. While hypervelocity stars are being ejected from galaxies, other cosmic events are tearing stars apart in even more dramatic fashion. Tidal disruption events occur when a star wanders too close to a supermassive black hole. Instead of being swallowed whole, the star is stretched and torn by the black hole's gravity. Remember spaghettification, that process we discussed earlier? Tidal disruption events are spaghettification happening to an entire star. The stellar material forms a long stream that wraps around the black hole. Some of this material falls in, while some is flung outward. The result is a brilliant flare of radiation that can outshine the entire galaxy for weeks or months. These events give astronomers a rare glimpse into the feeding habits of supermassive black holes. Most of the time, these black holes are dormant, surrounded by relatively little material to consume. But when a star strays too close, the black hole briefly wakes up and puts on a spectacular show. Tidal disruption events are relatively rare. In a typical galaxy, one might happen every 10,000 to 100,000 years. But because there are so many galaxies in the observable universe, astronomers detect several dozen of these events every year. Each one represents a star that existed for millions or billions of years, fusing hydrogen in its core, warming any planets that might have orbited it, perhaps even hosting life. And then, in a cosmic instant, all of that was torn apart by gravity and consumed by a black hole. This brings us to a broader point about cosmic violence. The universe is not a peaceful place. We live on a small planet orbiting a quiet star in a relatively calm region of a middling galaxy. Our local cosmic environment is about as safe as space gets. But even here, danger lurks. Even here, forces beyond our control could reshape our world or end it entirely. Consider the fact that our sun will not last forever. In about 5 billion years, it will exhaust the hydrogen fuel in its core. The core will shrink and heat up, while the outer layers expand outward. Our sun will become a red giant, swelling to perhaps 100 times its current size. Mercury will be consumed. Venus will be consumed. Whether Earth will be swallowed or merely scorched into a barren rock remains uncertain, but either way, our planet will become uninhabitable long before the sun reaches that stage. As the sun expands, it will also lose mass through stellar winds, streams of particles blowing outward into space. Planets that survive the red giant phase will drift into wider orbits as the sun's gravitational grip weakens. Eventually, the sun will shed its outer layers entirely, forming a beautiful cloud of gas called a planetary nebula. At the center will remain a white dwarf, the compressed core of the former sun, slowly cooling over trillions of years. This is the fate of our star. It is not a violent death by cosmic standards. There will be no supernova, no neutron star, no black hole. The sun is not massive enough for such dramatic endings. But for any life forms that still exist in our solar system at that time, the slow transformation of the sun will be plenty catastrophic. Of course, humanity has more immediate concerns than events 5 billion years in the future. Our more pressing cosmic threats operate on shorter timescales. Near-Earth objects, asteroids, and comets that pass close to our planet represent a danger we are only beginning to understand and address. The solar system is littered with debris left over from its formation 4.5 billion years ago. Most of this debris sits in the asteroid belt between Mars and Jupiter, or in the distant Kuiper belt beyond Neptune. But gravitational interactions can send these objects careening into the inner solar system on orbits that cross Earth's path. When that happens, we have what astronomers call a potentially hazardous object. Earth has been struck by large objects many times throughout its history. About 66 million years ago, an asteroid roughly 10 kilometers across slammed into what is now the Yucatan Peninsula of Mexico. The impact created a crater 180 kilometers wide. The explosion was billions of times more powerful than any nuclear bomb. Dust and debris were blasted into the upper atmosphere, blocking sunlight for months or years. Temperatures plummeted. Plants died. The dinosaurs, along with about 75% of all species on Earth, went extinct. This was not an isolated incident. Smaller impacts happen far more frequently. Every day, about 100 tons of space dust and small meteors fall to Earth, mostly burning up in the atmosphere. Larger objects capable of causing regional damage strike every few hundred to few thousand years. City-destroying impacts happen every few tens of thousands of years. Extinction. Level events occur every few 100 million years on average. We are working to identify these threats. Telescopes scan the sky every night, cataloging asteroids and calculating their orbits. NASA and other space agencies have tested technology to deflect incoming objects. In September 2022, a spacecraft deliberately crashed into a small asteroid moon called Dimorphos, successfully changing its orbit. This was proof that humans can, in principle, defend Earth against certain types of cosmic threats. But our detection capabilities are not perfect. Many potentially hazardous objects remain undiscovered. Objects coming from the direction of the sun are particularly hard to spot because the sun's glare blinds our telescopes. We could have only days or weeks of warning for certain types of impacts. And there are categories of threats, like long-period comets that spend most of their time in the outer solar system that we might not detect until they are already heading toward us at high speed. The universe is constantly reminding us that we are not in control. We build our civilizations and make our plans as if the ground beneath our feet will always be stable. But the planet we call home is a tiny island in a vast ocean of space, surrounded by forces that could sweep us away without any effort at all. Let us now explore something truly alien, a type of cosmic object so dense and so strange that it defies common experience. Neutron stars are the compressed cores of massive stars that have exploded as supernovae. When a star between about 8 and 25 times the mass of the sun reaches the end of its life, the outer layers are blasted away in a brilliant explosion, while the core collapses under its own gravity. What remains is a ball of neutrons, the subatomic particles found in atomic nuclei, packed so tightly that a single teaspoon of neutron star material would weigh about 6 billion tons. Neutron stars are typically only about 20 kilometers across, roughly the size of a city. Yet they contain more mass than our entire sun. This incredible density creates gravitational and magnetic fields far beyond anything found on Earth. The gravity at the surface of a neutron star is about 2 billion times stronger than Earth's gravity. If you somehow stood on a neutron star, the gravitational force would crush you flatter than paper in a fraction of a second. The magnetic fields of neutron stars are equally extreme. Typical neutron stars have magnetic fields trillions of times stronger than Earth's magnetic field. A special class called magnetars has fields even stronger, quadrillions of times greater than our planet's field. These magnetic fields can affect matter at the atomic level, distorting electron orbits and altering chemical bonds. Near a magnetar, the normal rules of chemistry simply do not apply. Neutron stars spin incredibly fast when they are first born, sometimes completing hundreds of rotations per second. As they spin, they emit beams of radiation from their magnetic poles. If Earth happens to be in the path of these beams, we see regular pulses of radio waves, X-rays or gamma rays. These spinning neutron stars are called pulsars, and they serve as some of the most precise clocks in the universe. The timing of their pulses is so regular that scientists use them to test theories of gravity and search for gravitational waves. Some neutron stars exist in binary systems with other stars. They can pull material from their companions, growing slowly over time. If a neutron star gains enough mass, it will collapse further, becoming a black hole. This transformation happens suddenly, with the neutron star vanishing behind an event horizon in the blink of an eye. One moment there is a dense ball of nuclear matter. The next moment there is only darkness. Neutron star mergers, when two neutron stars spiral together and collide, are among the most energetic events in the universe after the Big Bang itself. These collisions release enormous amounts of gravitational waves, ripples in the fabric of space-time that travel outward at the speed of light. In August 2017, astronomers detected gravitational waves from such a merger for the first time, along with electromagnetic radiation across the entire spectrum. This single event taught us more about neutron stars and heavy element production than decades of previous research. The merger also confirmed something remarkable. The collision of two neutron stars creates a kilonova, an explosion that forges elements heavier than iron. Gold, platinum, uranium, and many other heavy elements are produced in these cataclysmic events and scattered across space. The gold in your jewelry, the uranium in nuclear reactors, the lead in old paint, all of it was forged in the violent deaths of neutron stars billions of years ago. We are quite literally made from the remnants of cosmic catastrophes. Let us venture deeper into the strange corners of the cosmos. We have talked about objects of incredible density, but what about the opposite extreme? What about the emptiness that defines most of the universe? Space is not uniformly filled with matter. Galaxies and galaxy clusters are concentrated in vast cosmic structures, filaments and walls that stretch across hundreds of millions of light years. Between these structures lie cosmic voids, enormous regions of space that are almost completely empty. The largest known voids are more than 1 billion light years across, containing very few galaxies and almost no ordinary matter. To put this in perspective, imagine the entire Milky Way galaxy with its hundreds of billions of stars and countless planets. Now imagine traveling through space at the speed of light. It would take you 100,000 years to cross our galaxy from one side to the other. Now imagine a region of space where you could travel for hundreds of millions of years at light speed and encounter almost nothing. That is a cosmic void. That is the emptiness that makes up most of the universe. Inside these voids, the conditions are unlike anywhere else in the cosmos. The density of matter is so low that any hypothetical observers living there would see an almost completely dark sky. Distant galaxies would be few and far between, their light dimmed by the vast distances. The cosmic microwave background radiation, that faint glow left over from the Big Bang, would be slightly cooler in voids due to the lower density of matter affecting how light travels through space. Some scientists have proposed that advanced civilizations might deliberately move into cosmic voids to escape the dangers of denser regions. away from the gravitational chaos of galaxy clusters, away from supermassive black holes. And gamma-ray bursts, a void might seem like a safe haven. But the isolation would be almost unimaginable. The nearest neighbors would be impossibly far away. Communication at light speed would take hundreds of millions of years. For all practical purposes, a civilization in a void would be alone. The existence of voids tells us something important about how the universe evolved. Shortly after the Big Bang, matter was distributed almost uniformly throughout space. But tiny variations in density, quantum fluctuations from the earliest moments of existence, served as seeds for future structures. Over billions of years, gravity amplified these tiny differences. Regions that were slightly denser attracted more matter, becoming the galaxies and clusters we see today. Regions that were slightly less dense lost matter to their neighbors, becoming the voids. This cosmic web of structure grew from almost nothing, shaped by forces operating across the entire visible universe. The voids are still growing. As the universe expands and dark energy pushes everything apart, the empty regions are becoming emptier. The filaments and walls where galaxies congregate are being stretched thinner. In the far future, voids will dominate the cosmos, vast oceans of emptiness interrupted only by isolated islands of matter. Now let us consider something that has fascinated scientists and philosophers for centuries. Is there life beyond Earth? Are we alone in this vast cosmos, or is life common throughout the universe? The sheer size of the observable universe makes it seem unlikely that Earth is the only place where life exists. There are roughly 200 billion galaxies within the volume of space we can observe. Each galaxy contains hundreds of billions of stars. Recent discoveries tell us that nearly every star has planets. That means there are more planets in the observable universe than grains of sand on all the beaches of Earth. Among all those planets, some percentage must be rocky worlds orbiting in the habitable zones of their stars, where temperatures allow liquid water to exist on the surface. We have found thousands of such planets already, and we have barely begun to search. The galaxy is full of potentially habitable worlds. The question is whether any of them actually host life. On Earth, life appeared remarkably quickly after the planet became hospitable. The oldest evidence of life dates back almost 4 billion years, only a few 100 million years after the surface cooled enough for liquid water to exist. This rapid emergence suggests that life might form easily wherever conditions are right. If that is true, the universe should be teeming with living things. But here's the puzzle that has haunted scientists since it was first clearly stated by physicist Enrico Fermi in the 1950s. If life is common and has had billions of years to spread throughout the galaxy, where is everybody? This question is known as the Fermi paradox. Our galaxy is roughly 13 billion years old, and Earth formed only 4.5 billion years ago. That means there was plenty of time for other civilizations to arise before us. Even if intelligent life is rare, even if it only develops on one planet in a million, there should still be thousands of civilizations in the Milky Way alone. And if even a single civilization developed interstellar travel and started spreading across the galaxy, it could colonize the entire Milky Way in just a few million years. A blink of an eye in cosmic terms. Yet we see no evidence of alien civilizations. We have detected no radio signals. We have found no alien artifacts in our solar system. The sky is silent. The universe appears empty of intelligent life, at least within the volume we can observe. Many explanations have been proposed for this cosmic silence. Perhaps intelligent life is far rarer than we assume. Perhaps civilizations destroy themselves before they can spread to the stars. Perhaps they exist but have no interest in communication or expansion. Perhaps they are hiding. Perhaps we are the first intelligent species to arise in our galaxy. One possibility is particularly chilling. Perhaps the journey from simple life to intelligent civilization involves one or more extremely difficult steps, filters that most life forms never pass through. Scientists call this the Great Filter. If the Great Filter is behind us, meaning it was some early step in the development of life that we have already passed, then we might be rare survivors in a universe where most planets never get beyond simple microbes. But if the Great Filter is ahead of us, meaning it involves some challenge that advanced civilizations cannot overcome, then our future may be far shorter than we hope. What could such a filter be? Nuclear war? Climate change? artificial intelligence gone wrong, self-replicating nanotechnology, or perhaps something we have not even imagined yet. Every advanced civilization might eventually discover some technology or face some challenge that destroys them. The silence of the cosmos might be the silence of the graveyard, filled with the ruins of species that reached for the stars and fell. This interpretation of the Fermi paradox suggests that the universe might be littered with the remains of dead civilizations. Perhaps there were once great empires spanning hundreds of star systems, now reduced to rubble and memory. Perhaps there were alien philosophers and scientists who asked the same questions we ask, looked up at the same stars we see, and wondered if they were alone. And perhaps whatever killed them is waiting for us too. Of course, there are more optimistic possibilities. Perhaps intelligent civilizations choose to transcend physical existence, uploading themselves into simulations or forms of being we cannot detect. Perhaps they evolve beyond the need for communication or expansion. Perhaps the galaxy is full of life forms so alien that we would not recognize them even if we were looking right at them. The truth is that we do not know. We have exactly one example of a planet with life, our own, and exactly one example of intelligent civilization, ourselves. Drawing conclusions about the entire universe from a single data point is nearly impossible. We might be typical, or we might be freakishly unusual. Until we find other life or prove definitively that we are alone, the question will remain open. Let us shift our gaze now to something that exists at the boundary between science and speculation. What lies beyond the observable universe? We can see roughly 46 billion light-years in every direction, the distance light has traveled since the Big Bang, accounting for the expansion of space. But the universe almost certainly extends far beyond that horizon. Inflation theory, our best explanation for the uniformity and flatness of the cosmos, suggests that the universe underwent an incredibly rapid expansion in the first fraction of a second after the Big Bang. During this inflation, space expanded far faster than light, pushing regions that were once in contact far beyond each other's horizons. The observable universe might be just a tiny bubble in a much larger expanse. How much larger? The calculations are staggering. Some estimates suggest the full universe is at least 10 to the 23 times larger than the observable portion. That is a 1 followed by 23 zeros. Others suggest it might be infinite, extending forever in all directions with no edge or boundary. We might never know the true size because light from regions beyond our horizon will never reach us, no matter how long we wait. In an infinite universe, strange things become not just possible, but inevitable. If there is an unlimited amount of space, and matter is distributed randomly throughout that space, then every possible configuration of atoms must exist somewhere. This means there could be another Earth out there, identical to ours in every way, with another version of you reading these exact words at this exact moment. In fact, in an infinite universe, there would be an infinite number of such copies, all existing simultaneously at unimaginably vast distances. This idea is called the multiverse, though it differs from other multiverse concepts in physics. It is not about parallel dimensions or branching quantum timelines. It is simply the consequence of infinite space and finite possibilities. If you shuffle a deck of cards enough times, eventually you will repeat a sequence. If you have infinite space for atoms to arrange themselves, eventually every arrangement must occur. The multiverse is deeply unsettling for many people. It suggests that you and everything you experience might be duplicated countless times throughout reality. It undermines the sense that our lives and choices are unique and meaningful. It stretches our concepts of identity and individuality to the breaking point. But we should be careful not to confuse speculation with established science. We do not know that the universe is infinite. We do not know that matter is distributed randomly throughout all of space. The multiverse remains a hypothesis, not a proven fact. It is possible that the universe has some structure or boundary we have not yet detected. It is possible that our existence is unique after all. What we do know is that the universe is vastly larger and stranger than our ancestors could have imagined. Every advance in astronomy has revealed a cosmos bigger and more complex than what came before. There is no reason to think we have reached the end of that process. Future discoveries might reveal depths of reality that make our current understanding look primitive. Let us explore another boundary, this time between matter and antimatter. For every particle of matter in the universe, there exists a corresponding antiparticle with opposite charge. Electrons have anti-electrons called positrons. Protons have antiprotons. When matter and antimatter meet, they annihilate each other completely, converting their mass into pure energy according to Einstein's famous equation. Antimatter is real. We create it in particle accelerators every day. Positrons are used in medical imaging through PET scans. But here is the mystery. The universe appears to be made almost entirely of matter. Where is all the antimatter? When the Big Bang occurred, matter and antimatter should have been created in equal amounts. They should have annihilated each other completely, leaving behind only radiation. There should be no stars, no planets, no people. Yet here we are. Somehow, in the first moments after the Big Bang, matter won a tiny victory over antimatter. For every billion antiparticles, there were 1,000,001 particles. After the Great Annihilation, that one particle per billion survived. And those survivors make up everything we see today. We do not fully understand why matter won this victory. It requires a violation of certain symmetries in physics, differences between matter and antimatter that we have not completely identified. This is one of the great unsolved problems. In cosmology, the existence of stars and galaxies and people depends on it, yet we cannot explain it. Some theories suggest that regions of antimatter might exist somewhere in the universe, separated from matter regions by vast distances. If such antimatter galaxies exist, they would look identical to matter galaxies. Light is the same whether emitted by matter or antimatter. We would have no way of knowing until something from those regions reached us. And if it did, the meeting would be explosive. Imagine a rogue antimatter object drifting into our solar system. Even a small antimatter asteroid, perhaps just a few meters across, would release energy equivalent to a large nuclear bomb when it collided with our atmosphere. The matter in the air would meet the antimatter in the rock, and both would convert entirely to radiation. Larger antimatter objects could be far more destructive. The odds of this happening are extremely small, perhaps essentially zero. We have no evidence that macroscopic antimatter exists anywhere in our region of the universe. But the mystery of why matter dominates remains unsolved. Until we understand it, we cannot be certain what other surprises the cosmos might hold. Now let us consider the strange relationship between space and time. Einstein showed us more than a century ago that space and time are not separate things, but rather two aspects of a single entity called space-time. Gravity is not a force pulling objects together, but rather the curvature of space-time caused by the presence of mass and energy. Massive objects like stars and planets bend the fabric of reality around them, and other objects follow the curves of that bent fabric. This understanding has been confirmed by countless experiments and observations. GPS satellites have to account for time running slightly faster in orbit than on Earth's surface because Earth's gravity slows time down. Light from distant stars bends as it passes near the sun, an effect observed during solar eclipses. Gravitational waves, ripples in space-time caused by accelerating masses, have been detected directly. But Einstein's equations also predict things we find deeply disturbing. They predict black holes, regions where space-time curves so extremely that nothing can escape. They predict singularities, points where density becomes infinite, and our understanding of physics breaks down. They suggest the possibility of wormholes, tunnels through space-time that could connect distant regions of the universe. Wormholes remain purely theoretical. We have never observed one, and we do not know if they can exist in the real universe. Time verschwundenes. If they do exist, they would require exotic matter with negative energy to keep them open, something we have never found. They might form naturally but collapse too quickly for anything to pass through. Or they might be stable enough for travel but lead to paradoxes that physics does not allow. The idea of wormholes connects to one of the most mind-bending possibilities in all of physics: time travel. If wormholes could connect different points in time as well as space, they might allow travel into the past. This seems to violate our basic understanding of cause and effect. How can you go back and change something that has already happened? Physicists have proposed various resolutions to these paradoxes. Perhaps the laws of physics prevent any action that would change the past. Perhaps traveling back in time creates a parallel timeline leaving the original intact. Perhaps closed time-like curves, the technical term for paths through space-time that loop back on themselves, simply cannot exist in nature. Whatever the truth, the mere fact that our best physical theories allow for such strange possibilities tells us that space-time is far more complex than our everyday experience suggests. We walk through space and experience time flowing from past to future, and we assume this is simply how reality works, but the underlying structure might be stranger and more flexible than we ever imagined. Let us turn now to something that connects the very small to the very large. Quantum mechanics, the physics of atoms and subatomic particles, describes a world very different from the one we experience at human scales. Particles exist in superpositions of multiple states until they are measured. Effects can happen instantaneously across vast distances through a phenomenon called entanglement. The very act of observation changes the system being observed. These quantum behaviors seem confined to the microscopic world. A single electron can be in two places at once, but a baseball cannot. A pair of entangled photons can share information instantly, but we cannot use this to send messages faster than light. The strangeness of quantum mechanics appears to wash out at larger scales, hidden beneath the classical physics that describes our everyday experience. But here's the thing, the entire universe emerged from a quantum state. In the earliest moments after the Big Bang, the cosmos was so small and so hot that quantum effects dominated everything. The large-scale structure of the universe today, the distribution of galaxies across billions of light years, traces back to quantum fluctuations in that primordial fireball. The tiny and random jitters of quantum mechanics have been stretched to cosmic proportions. This means that quantum weirdness is not just a curiosity of the subatomic world. It is written into the fabric of reality at the largest scales. The universe we see is a quantum phenomenon, born from uncertainty and probability, shaped by laws that we are only beginning to understand. Some physicists take this further. The many worlds interpretation of quantum mechanics suggests that every quantum measurement causes the universe to branch into multiple copies, one for each possible outcome. If this interpretation is correct, there are countless parallel universes splitting off from ours every moment, each containing a slightly different version of reality. Every choice you make, every quantum event that occurs anywhere in the cosmos, creates new branches in an ever-expanding tree of possibility. The many worlds interpretation solves certain problems in quantum mechanics, but it creates philosophical challenges of its own. How do we define probability in a multiverse where every outcome actually happens? What does it mean to be you if there are infinite versions of you experiencing every possible life? These questions may have no answers, at least none that satisfy our intuitions about identity and choice. Whether or not many worlds is the correct interpretation, quantum mechanics has revealed a universe far stranger than classical physics prepared us for. Reality at its most fundamental level operates according to rules that defy common sense. Particles pop in and out of existence in the vacuum. Cats can be simultaneously alive and dead until we open the box. Information can be teleported from one place to another by exploiting quantum entanglement. The cosmos is weird all the way down. Let us now explore the violence that birthed everything we know. The Big Bang was not an explosion in space, but rather an explosion of space. There was no empty void waiting to be filled. Space and time themselves came into existence at that moment. Everything that would ever exist was compressed into an unimaginably hot and dense state, a singularity where our physics breaks down completely. What caused the Big Bang? We do not know. Some theories suggest our universe budded off from a parent universe through a quantum fluctuation. Others propose that universes naturally pop into existence from pure nothing, with the total energy of a universe being zero when you account for both positive energy like matter and negative energy like gravity. Still others suggest that time had no beginning, that what we call the Big Bang was simply a transition from a previous state of existence. The moments immediately after the Big Bang are better understood, though still filled with mysteries. During the first tiny fraction of a second, the universe underwent inflation, expanding far faster than light and smoothing out any irregularities from the initial singularity. This inflation explains why the cosmos looks the same in all directions and why space appears geometrically flat rather than curved. As the universe cooled, the fundamental forces separated out from a unified state. First, gravity distinguished itself from the other forces, then the strong nuclear force, then the electromagnetic and weak forces. Particles formed from the cooling soup of energy. Within the first few minutes, the lightest elements like hydrogen and helium were forged in the cosmic furnace. For the next 400,000 years, the universe was filled with a hot plasma of particles and radiation. Light could not travel freely because it kept being absorbed and re-emitted by the charged particles. Then, as temperatures dropped below about 3,000 degrees, electrons combined with atomic nuclei to form neutral atoms. Suddenly, light could travel through space unimpeded. This moment, called recombination, released the cosmic microwave background radiation that we can still detect today. The cosmic microwave background is the oldest light in the universe. It shows us what the cosmos looked like when it was only 400,000 years old, a smooth bath of radiation with tiny variations in temperature. Those temperature variations correspond to slightly denser and slightly less dense regions. Over billions of years, the denser regions grew into the galaxies and clusters we see today, while the less dense regions became the cosmic voids. After the cosmic microwave background was released, the universe entered a period called the Cosmic Dark Ages. There were no stars yet, no galaxies, no sources of light, except the fading glow of the Big Bang. For hundreds of millions of years, the cosmos was a dark and quiet place. Matter slowly gathered under the influence of gravity, forming the first clumps that would eventually ignite as the first stars. The first stars were unlike anything in the modern universe. They were made of pure hydrogen and helium, lacking the heavier elements that later generations of stars would produce. They were massive, perhaps hundreds of times the mass of our sun, and they burned hot and fast, living only a few million years before exploding as supernovae. These first explosions seeded the cosmos with carbon, oxygen, iron, and all the other elements needed to build rocky planets and living things. Generation after generation of stars lived and died, each one adding more heavy elements to the cosmic inventory. The universe grew richer and more complex over time. Galaxies merged and grew. Black holes formed and fed. The stage was set for smaller, longer-lived stars like our sun to form, surrounded by rocky planets made from the ashes of ancient stellar deaths. Our own solar system formed about 4.5 billion years ago from a cloud of gas and dust enriched by countless previous stellar generations. The heavy elements in your body, the iron in your blood, the calcium in your bones, the carbon that forms the backbone of every organic molecule, all of it was forged in the hearts of stars that died before the sun was born. You are quite literally made of star stuff, atoms that have journeyed through cosmic fire and stellar death to assemble temporarily as you. This realization connects us to the violence of the cosmos in a deeply personal way. We are not just observers of the universe, we are participants, made from the same materials and shaped by the same forces. The story of the cosmos is our story. The birth and death of stars is our heritage. The terrifying violence of space has made us possible. Let us now consider some of the more exotic theoretical objects that might exist in the universe. We have talked about black holes and neutron stars, objects whose existence is well established by observation. But physics allows for even stranger things, entities that push the boundaries of what we can imagine. Strange stars might exist as an alternative to neutron stars. In a normal neutron star, the pressure is not quite high enough to break neutrons down into their constituent quarks. But at slightly higher pressures, neutron matter might transform into something called strange quark matter, containing roughly equal numbers of up, down, and strange quarks. If strange quark matter is more stable than ordinary matter, which is an open question, then strange stars would represent the true ground state of nuclear material. Even more exotic are objects called quark stars, where the pressure is high enough to create a soup of freely moving quarks rather than distinct particles. And beyond that, there might be preon stars made of the hypothetical smaller particles that quarks themselves might be made of, if quarks are not truly fundamental. These objects remain speculative, but they remind us that we do not fully understand matter at its most extreme densities. White holes are the theoretical time reversal of black holes. While a black hole is a region of space that nothing can leave, a white hole would be a region that nothing can enter. Material would only flow outward from a white hole, never inward. Einstein's equations allow for white holes, but we have never observed one. Many physicists believe they cannot exist in our universe because they would violate the second law of thermodynamics, creating a decrease in entropy that nature does not permit. Cosmic strings are another theoretical possibility, one-dimensional defects in space-time left over from phase transitions in the early universe. Think of them like cracks that form when water freezes into ice. If cosmic strings exist, they would be incredibly thin but incredibly massive, stretching across vast distances and bending space-time around them. A cosmic string passing near Earth would cause strange gravitational effects, perhaps even creating duplicate images of objects behind it. We have searched for evidence of cosmic strings in the cosmic microwave background and in gravitational lensing, but so far we have found nothing definitive. The theoretical landscape of physics contains many such possibilities, objects and phenomena that might or might not exist in the real universe. Some will eventually be confirmed by observation, others will be ruled out. Still, others may remain forever beyond our ability to test. The universe is under no obligation to be simple enough for us to understand completely. Let us return now to something closer to home but no less terrifying. Our own sun, the star that makes life on Earth possible, is capable of violence that could devastate our technological civilization. The sun is constantly releasing energy through nuclear fusion, converting hydrogen into helium in its core. This energy radiates outward, eventually reaching the surface where it is released as light and heat. But the sun also produces solar flares, sudden releases of magnetic energy that accelerate particles to enormous speeds and blast them into space. Large solar flares can interfere with radio communications, damage satellites, and create beautiful auroras in the night sky. But the truly dangerous events are coronal mass ejections, massive bubbles of plasma and magnetic field that are thrown outward from the sun. When these bubbles are directed at Earth, they can cause geomagnetic storms that affect our planet in significant ways. In 1859, a massive solar storm called the Carrington event struck Earth. At that time, the most advanced electrical technology was the telegraph. The storm induced such powerful currents in telegraph wires that operators received shocks, and some equipment caught fire. Aurora displays were visible as far south as the Caribbean. The sun had demonstrated its ability to reach across space and affect our technology. If a Carrington-level event happened today, the consequences would be far more severe. Our civilization depends on electrical grids, satellites, and computer networks that are all vulnerable to geomagnetic disturbances. A major solar storm could knock out power grids across entire continents, taking months or years to repair. Satellites could be damaged or destroyed. GPS navigation would fail. Communication, networks would collapse. The economic cost has been estimated in the trillions of dollars. The human cost could be much higher if essential services like hospitals and water treatment plants lost power for extended periods. We know that storms larger than the Carrington event have occurred in the past. Tree ring records show evidence of massive solar particle events thousands of years ago. The sun is capable of outbursts that would make 1859 look mild by comparison, and we have no way to stop them. We can predict solar activity to some degree and give satellite operators and power grid managers a few hours of warning. But ultimately, we are at the mercy of our star. Speaking of stars, let us consider what happens when they die in the most spectacular way possible. We have discussed supernovae before, but these explosions deserve a closer look because they represent some of the most powerful events in the universe. A supernova occurs when a massive star runs out of fuel and its core collapses, or when a white dwarf in a binary system gains enough mass from its companion to trigger runaway nuclear fusion. In either case, the result is an explosion that briefly outshines an entire galaxy. For a few weeks, a single dying star can produce as much light as hundreds of billions of normal stars combined. The energy released in a supernova is almost beyond comprehension. About 1% of the explosion's total energy is released as visible light, and even that is enough to outshine galaxies. Another 99% is carried away by neutrinos, ghostly particles that barely interact with matter and can pass through entire planets without noticing. The remaining fraction of a percent is kinetic energy, the physical force of the explosion that blasts the outer layers of the star into space at speeds up to 10% of the speed of light. If a supernova occurred close enough to Earth, it would be a catastrophe. The exact danger depends on the type of supernova and the distance, but generally, an explosion within about 30 light years could cause serious problems. The initial burst of radiation would be absorbed by our atmosphere, but high-energy cosmic rays would continue arriving for years, damaging the ozone layer and increasing the radiation dose at the surface. Mass extinctions could follow. The good news is that no stars close enough to pose a danger are likely to explode anytime soon. The nearest candidates are too far away or not massive enough or not close enough to the end of their lives. Betelgeuse, the red supergiant in the constellation Orion, will explode someday and will be bright enough to be visible during the day, but at about 700 light-years away, it poses no threat to Earth. The bad news is that we cannot be completely certain about stellar evolution. Stars are complex systems that can behave in unexpected ways, and our solar neighborhood changes over time as the Sun orbits the galactic center. Stars that are far away today might have been closer in the past, or might become closer in the future. Over billions of years, close supernovae are essentially inevitable. Let us consider another type of stellar death, one that is quieter but no less significant. Planetary nebulae are not really nebulae in the traditional sense. They are the glowing shells of gas expelled by dying sun like stars in the later stages of their evolution. When a star like our Sun exhausts the hydrogen in its core, it begins burning helium and expands into a red giant. The outer layers become unstable and are gradually ejected into space. Intense radiation from the exposed core ionizes this ejected material, causing it to glow in beautiful colors. The result is a planetary nebula, a cosmic art display marking the death of a star. Planetary nebulae come in remarkable shapes: rings, hourglasses, butterflies, and complex patterns that astronomers are still working to understand. The shapes depend on the star's rotation, magnetic field, and whether it has companion stars affecting the geometry of the ejection. Some of the most beautiful images ever, taken by space telescopes, show planetary nebulae in their full glory. At the center of each planetary nebula is the remnant core of the dead star, now a white dwarf. This dense sphere of carbon and oxygen no longer generates energy through fusion. It simply cools over time, radiating away the heat accumulated during its active life. Eventually, trillions of years from now, white dwarfs will cool to the temperature of the surrounding space and become invisible black dwarfs. But no black dwarfs exist yet because the universe is not old enough. Our Sun will undergo this process in about 5 billion years. Earth may or may not survive the red giant phase, but either way, any descendants of humanity who remain in the solar system will have to find a new home long before then. The Sun's luminosity increases over time even during its main sequence life, and Earth will likely become uninhabitable within about 1 billion years as the oceans begin to evaporate. 1 billion years might seem like a long time, but it is short compared to the age of the universe. Life on Earth has existed for nearly 4 billion years already. Complex life has existed for about 600 million years. Human civilization has existed for perhaps 10,000 years. In the grand scheme of things, our time in the Sun is limited. Whatever destiny awaits humanity, it will not include our current home for much longer in cosmic terms. Let us explore another aspect of cosmic violence that happens on a grand scale. Galaxy collisions are among the most spectacular events in the universe, involving hundreds of billions of stars over timescales of hundreds of millions of years. Despite the vast distances between galaxies, they do sometimes collide. Gravity pulls them together across millions of light years. When galaxies meet, something remarkable happens. Although each galaxy contains hundreds of billions of stars, actual stellar collisions are extremely rare because stars are so tiny compared to the distances between them. Instead, the galaxies pass through each other like two swarms of bees, their stars intermingling but rarely touching. What does change dramatically is the gas between the stars. This interstellar medium gets compressed and shocked as the galaxies collide, triggering massive waves of star formation. New stars ignite by the millions. The collision can create brilliant starbursts that light up the combined galaxy far beyond its normal brightness. The shapes of the colliding galaxies are also transformed. graceful spirals become tangled messes. Tidal forces stretch out long streamers of stars that arc across hundreds of thousands of light years. Computer simulations show beautiful patterns forming and dissolving as the collision plays out over hundreds of millions of years. Our own Milky Way is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. In about 4 billion years, these two galaxies will begin their merger, eventually combining into a single giant elliptical galaxy that astronomers have nicknamed Milkdromeda. The collision will transform the night sky if anyone is around to see it. Andromeda will grow larger and larger until it fills much of the visible sky. New stars will form in great waves. The familiar constellations will be distorted beyond recognition. Individual stars like our Sun will likely survive the collision just fine. The odds of another star passing close enough to disrupt our solar system are very small, but the character of our galactic home will change completely. The orderly spiral structure of the Milky Way will be lost. Our descendants, if they exist, will live in a very different cosmos than we do. Galaxy collisions are happening all over the universe right now. Telescopes have captured images of colliding galaxies in various stages of their merger, providing a gallery of cosmic violence in action. These images show us what our own future might look like, though the timescales involved dwarf human experience so completely that it is hard to feel any urgency about events 4 billion years from now. Let us now consider the mystery of fast radio bursts, one of the newest puzzles in astronomy. These are brief pulses of radio waves coming from distant galaxies lasting only milliseconds but releasing as much energy as the Sun produces in a day. First detected in 2007, fast radio bursts have since been observed hundreds of times, but their origin remains uncertain. Various explanations have been proposed. Some bursts might come from magnetars, those highly magnetized neutron stars we discussed earlier. Others might be produced by colliding compact objects or even more exotic phenomena we have not imagined. One burst was found to repeat irregularly, ruling out explanations involving events that destroy the source. But other bursts appear to be one-time occurrences, suggesting multiple mechanisms might be at work. For a brief period, some people wondered if fast radio bursts might be signals from alien civilizations. The idea was exciting, if unlikely. When you detect something you do not understand, it is natural to consider every possibility. But as astronomers have gathered more data, natural explanations have become increasingly favored. Fast radio bursts join the long list of cosmic phenomena that initially seemed mysterious, but ultimately turned out to be natural processes we did not previously know about. This pattern repeats throughout the history of astronomy. Strange signals and unusual objects are discovered, briefly raising the possibility of artificial origins, then eventually explained by new physics or previously unknown natural processes. The universe is constantly teaching us that nature is more creative than we imagined, capable of producing phenomena that initially seem impossible. Let us talk about something that connects the observable universe to the quantum realm in ways we are only beginning to explore. Black hole information paradox presents one of the deepest problems in theoretical physics, a conflict between general relativity and quantum mechanics that threatens our understanding of how the universe works. According to quantum mechanics, information cannot be destroyed. The state of a physical system can always in principle be reversed, like playing a movie backward. Everything that happens can be undone, at least in theory. But black holes seem to violate this principle. When something falls past the event horizon, it appears to be lost forever. When the black hole eventually evaporates through Hawking radiation, the radiation that comes out appears to be completely random, containing no information about what fell in. This creates a paradox. Either information is destroyed when black holes evaporate, violating quantum mechanics, or something about our understanding of black holes is wrong, violating general relativity. Both theories are among the most successful and well-tested in all of physics. The conflict between them points to something deep about reality that we do not yet understand. Physicists have proposed many solutions to this paradox. Perhaps information is somehow encoded in the Hawking radiation after all, in ways that are extremely difficult to detect. Perhaps information is stored on the event horizon itself, in a kind of hologram that preserves everything that fell in. Perhaps black holes do not fully evaporate, but instead leave behind remnants that contain the missing information. Perhaps our understanding of space-time itself needs to be revised. Recent theoretical developments suggest that black holes might be far more complex than we thought. The event horizon might be surrounded by a firewall of high-energy particles that would incinerate anything falling in, contradicting the prediction that crossing the horizon should be uneventful. Or perhaps quantum effects modify the very structure of spacetime near black holes, creating something called a fuzzball instead of a classical black hole. These ideas are difficult to test because we cannot observe the inside of a black hole. Whatever happens beyond the event horizon is hidden from us by definition. We can only infer what might be happening from theoretical calculations and thought experiments. The black hole information paradox remains unsolved, a reminder that our understanding of the universe is incomplete. Let us shift our attention to the cosmic microwave background once more, because this ancient light contains clues about mysteries beyond what we have discussed. When scientists map the tiny temperature variations in the cosmic microwave background, they find patterns that match theoretical predictions remarkably well. But there are also hints of anomalies, features that do not quite fit our standard models. One such anomaly is the cold spot, an unusually large region of the sky that is slightly cooler than expected. Various explanations have been proposed, from a supervoid, an unusually empty region of space along the line of sight, to more exotic possibilities involving collisions with other universes. The cold spot might just be a statistical fluctuation, the kind of variation you expect when looking at random patterns, or it might be telling us something profound about cosmic structure. Another anomaly is the apparent alignment of the largest scale features in the cosmic microwave background, with the plane of the solar system and the direction of Earth's motion through space. This is strange because there should be no connection between local astronomical features and patterns imprinted on the sky when the universe was only 400,000 years old. The alignment might be coincidence, or it might indicate some unknown effect that our models do not account for. These anomalies could be nothing. Statistical fluctuations and measurement errors can create apparent patterns that disappear with better data, but they could also be hints of new physics, windows into aspects of reality that our current theories miss. Science progresses by paying attention to such hints, following them where they lead, and being willing to revise our understanding when the evidence demands it. Let us explore the concept of entropy more deeply, because it underlies the ultimate fate of everything. Entropy is a measure of disorder, of the number of ways a system can be arranged while still looking the same from the outside. A neatly stacked deck of cards has low entropy because there is only one way to arrange the cards in that specific order. A shuffled deck has high entropy because there are countless arrangements that count as shuffled. The second law of thermodynamics states that entropy always increases in closed systems. Things naturally become more disordered over time. Ice melts, hot coffee cools, buildings crumble, stars burn out. This tendency toward disorder is not just a rule of physics, but a statistical inevitability arising from the vastly greater number of disordered states compared to ordered ones. The increase of entropy is responsible for the arrow of time, the fact that we experience time flowing in one direction. The past is when entropy was lower. The future is when entropy will be higher. We remember the past but not the future because memory is a low entropy state that gets established by physical processes moving from ordered to disordered configurations. The ultimate high entropy state is heat death, which we discussed earlier. When the universe reaches maximum entropy, no further change will be possible. There will be no temperature gradients to drive energy flow. No structures will exist to store information or perform computation. Time itself might become meaningless because nothing would distinguish one moment from another. But here's a strange twist. The universe began in an extremely low entropy state. The Big Bang was not a chaotic explosion, but a remarkably ordered event, with matter distributed almost uniformly and gravitational energy nearly zero. This is puzzling because low entropy states are improbable. The universe started in a highly unlikely configuration and has been becoming more disordered ever since. Why did the universe begin with such low entropy? This is called the past hypothesis, and it remains one of the deepest mysteries in physics. Some theories suggest that inflation created the low entropy initial conditions. Others propose that our universe is part of a larger multiverse where low entropy regions occasionally arise by chance. Still, others argue that the question itself is misguided, that the apparent low entropy of the early universe is an artifact of how we define entropy in gravitating systems. Whatever the explanation, the low entropy beginning is essential for everything we experience. Without an entropy gradient, there would be no arrow of time, no evolution, no possibility of life or thought. The universe's strange starting point made everything possible. Let us now talk about something that spans the gap between astronomy and biology. Panspermia is the idea that life might spread between worlds, carried by asteroids, comets, or even dust, blown by stellar radiation. If this idea is correct, life on Earth might have originated elsewhere, perhaps on Mars or even outside our solar system. We know that material is exchanged between planets. Impacts can blast rocks off one world and send them on journeys through space that end on another world. Martian meteorites have been found on Earth. By the same logic, Earth rocks must have reached Mars. If those rocks carried dormant microorganisms, life could have survived the journey and seeded a new world. Laboratory experiments have shown that certain bacteria and spores can survive conditions similar to space travel. Vacuum, extreme cold, intense radiation. Some organisms have survived years of exposure outside the International Space Station. The journey between Earth and Mars could take millions of years, but with the right protection inside a rock, microbial, life might survive. If panspermia has occurred, it would mean that all life in our solar system might share a common origin. Mars and Earth might be biological siblings, seeded by the same ancestral organisms. Or life might have originated on Mars when that planet was warmer and wetter, then traveled to Earth after conditions on Mars deteriorated. We might all be Martians. Extending panspermia to interstellar scales is more speculative. The distances between stars are vastly greater than the distances between planets. Travel times would be millions of years at minimum, but the universe is billions of years old, and even slow processes can accomplish a lot given enough time. Tardigrades, those hardy microscopic animals that can survive extreme conditions, have been proposed as possible interstellar travelers, protected inside comets or ice grains. If interstellar panspermia is possible, life might be far more widespread than we realize. Habitable worlds throughout the galaxy might have been seeded from a few original sources, creating a connected biosphere spanning light years. This does not solve the mystery of how life originated in the first place, but it does suggest that once life gets started somewhere, it might spread far and wide. Let us return to the Fermi paradox once more because its implications are so profound. We have been sending radio signals into space for about a century. Our television broadcasts, radar pulses, and intentional messages have created an expanding bubble of electromagnetic noise centered on Earth. Any civilization within 100 light years with sufficiently sensitive equipment could detect our presence. But we have been listening too, and we have heard nothing. The search for extraterrestrial intelligence, or SETI, has monitored the skies for decades looking for artificial signals among the natural radio noise of the cosmos. Despite covering large portions of the sky and many radio frequencies, no confirmed alien signal has ever been detected. This silence is strange because signals travel at the speed of light. Even if alien civilizations are rare and widely separated, the first civilization to develop radio technology would have had billions of years to fill the galaxy with signals. Unless they all choose to be silent, unless they all destroy themselves before going interstellar, unless there is something fundamentally wrong with our assumptions, we should have heard something by now. Various resolutions have been proposed, some hopeful and some disturbing. Perhaps aliens communicate using technologies we have not discovered yet, methods that are undetectable with our current equipment. Perhaps they have moved beyond radio to something more efficient, like tightly beamed laser communication or gravitational waves or quantum effects we do not understand. Perhaps they are all around us, communicating constantly, and we just cannot pick up their calls because we are using the cosmic equivalent of smoke signals in an age of fiber optics. Or perhaps the galaxy really is as empty as it appears. Perhaps the emergence of intelligent life requires such a specific and unlikely sequence of events that we truly are alone. Perhaps every other civilization that ever existed has already gone extinct, their lights extinguished by war or disaster or choices we cannot imagine. Perhaps we are the first, destined to fill the silence ourselves if we can survive long enough. The implications of either possibility are staggering. If the galaxy is full of intelligent life, we need to understand why we cannot detect it and what that means for our future. If we are alone, we carry a responsibility that defies comprehension. We are the only ones who can give the universe meaning, the only minds capable of understanding and appreciating the cosmos. Either way, our place in the universe is stranger and more significant than our ancestors could have imagined. Let us consider one more terrifying possibility before we draw our journey to a close. What if the universe itself is not what it appears to be? What if everything we experience, every star and planet and person, is a simulation running on some unimaginably powerful computer? This idea might sound like science fiction, but it has been seriously considered by philosophers and physicists. The argument goes something like this: if civilizations can survive long enough to develop technology far beyond our own, they might eventually be able to simulate entire universes, complete with conscious beings who believe they are real. If such simulations are possible, and if advanced civilizations tend to run many of them, then the number of simulated universes would vastly outnumber the single real universe. By simple probability, any given conscious being is more likely to be in a simulation than in base reality. If we are in a simulation, what would that mean? The beings running our universe might be conducting experiments, studying how civilizations develop under different conditions. They might be entertainment, cosmic video games for minds we cannot comprehend. They might be archival recreations of their own past, archaeological digs into the history of their civilization. Or they might have purposes we cannot imagine, motives that make no sense to beings at our level of understanding. A simulated universe would not necessarily be different from a real one in any detectable way. The simulation could be perfect, indistinguishable from physical reality. Or it could be an approximation, with shortcuts and simplifications that might reveal themselves under close enough examination. Some physicists have speculated that certain features of our universe, like the speed of light acting as a maximum velocity or the discrete nature of quantum mechanics, might be signs of computational limits in an underlying simulation. This is speculation, of course, not established science. We have no way to test whether we are in a simulation. We have no evidence either for or against the hypothesis, but the very possibility changes how we think about reality. If we cannot be certain that our universe is physically real, what does that do to our understanding of existence, meaning, and purpose? Perhaps it does not matter. Whether we are made of atoms or of information, our experiences are real to us. Our joys and sorrows, our loves and losses, our curiosity about the cosmos. These are genuine regardless of the underlying substrate. A simulated sunset is still beautiful. A simulated question is still worth asking. And a simulated search for truth is still noble. Now let us draw back and consider what we have learned on this journey through the strange and terrifying universe. We have encountered black holes, those prisons of gravity that trap even light. We have witnessed gamma ray bursts, cosmic explosions that can sterilize planets across thousands of light years. We have contemplated vacuum decay, the possibility that reality itself could be erased without warning. We have explored dark matter and dark energy, the invisible substances that dominate the cosmos and control its fate. We have wandered with rogue planets through the darkness between stars. We have felt the pull of the great attractor, drawing our galaxy toward an unknown destination. We have peered into the far future and seen heat death, the slow cooling of everything into eternal stillness. We have marveled at hypervelocity stars flung from galactic centers and tidal disruption events that tear stars apart. We have watched the sun's violence and worried about solar storms. We have witnessed supernovae and planetary nebulae, the spectacular deaths of stars. We have collided galaxies and detected fast radio bursts from distant sources. We have puzzled over the black hole information paradox and the anomalies in the cosmic microwave background. Time for Wastasashin. We have followed entropy toward its ultimate triumph and wondered why the universe began so ordered. We have considered panspermia and the Fermi paradox, and the possibility that we might be alone. Throughout all of this, certain themes keep emerging. The universe is violent. It does not care about us. Forces beyond our control could end human civilization or even all life on Earth. and the cosmos would not notice. We live on a small rock orbiting an ordinary star in the suburbs of a typical galaxy, one among hundreds of billions of galaxies in the observable universe alone. Our importance on the cosmic scale is essentially zero. And yet there is another way to see our situation. Yes, the universe is terrifying, but it is also beautiful beyond description. The same forces that could destroy us have also created us. Stars had to live and die to produce the atoms in our bodies. Supernovae had to explode to scatter those atoms through space. Gravity had to gather them into new stars and planets where chemistry could become biology, and biology could become thought. We are the universe looking at itself. We are matter that has organized itself into patterns complex enough to ask questions about their own existence. We are the cosmos becoming aware of its own vastness and strangeness and terror. This is not nothing. This might be the most remarkable thing that has ever happened in all of cosmic history. The terrifying things in space are not just threats to fear. They are also sources of wonder. Black holes stretch our understanding of physics to its limits. Gamma-ray bursts reveal the extreme conditions where matter and energy transform in ways we are only beginning to comprehend. Even the possibility of vacuum decay, as disturbing as it is, opens a window into the deep structure of reality, the quantum fields that underlie everything we experience. The cosmos is a teacher, albeit a harsh one. Every danger we discover is also a lesson about how the universe works. Every mystery we encounter is an invitation to expand our knowledge. Every limit we find is a challenge to push our understanding further. The terrifying strangeness of space is not separate from its beauty and fascination. They are the same thing seen from different angles. Consider what it means that we can even have this conversation. A species that evolved on the African savanna to hunt animals and gather plants has figured out the age of the universe, the composition of distant stars, the structure of atoms, and the curvature of space-time. We have built telescopes that can see galaxies billions of light years away and accelerators that can recreate conditions from the first moments after the Big Bang. We have sent robots to other planets and spacecraft to the edges of the solar system. We have detected gravitational waves from colliding black holes and imaged the shadows of supermassive black holes in distant galaxies. This is extraordinary. This is unprecedented. As far as we know, nothing like this has ever happened before in the history of the cosmos. And we are just getting started. The discoveries of the next century will make our current knowledge look primitive. The questions we cannot even formulate yet will become the puzzles that keep future generations up. At night, the terrifying things in space do not diminish us. They contextualize us. They show us our place in a universe far larger and stranger than we could have imagined. They humble us, yes, but they also inspire us. Every threat we identify is a problem we might someday solve. Every danger we understand is a danger we can prepare for. Every mystery we probe is a step toward knowing the universe as it truly is. And there is something else, something that emerges from contemplating our cosmic insignificance. Precisely because we are so small and the universe is so vast, precisely because we exist for such a brief moment in cosmic time, precisely because there may be no one else out there to witness the grandeur of creation, our existence takes on a meaning it would not otherwise have. We matter not despite the cosmic scale, but because of it. We are rare. We are precious. We are the universe's way of knowing itself. This does not mean we should ignore the dangers. Asteroid impacts, solar storms, climate change, and our own technological creations all pose real threats that deserve serious attention. We should scan the skies for dangerous objects. We should protect our infrastructure from solar activity. We should be prudent stewards of our planet and our technology. The universe will not save us from ourselves. If we destroy our civilization through war or environmental collapse or unintended consequences of our inventions, the stars will continue to shine as if nothing happened. But we should also not live in fear. The cosmic timescales we have discussed are mostly far beyond human lifetimes. The sun will not become a red giant for billions of years. The Andromeda collision is 4 billion years away. Heat death is so far in the future that the numbers become meaningless. On any timescale that matters for human lives and human planning, the universe is a reasonably safe place. The dangers are real, but mostly distant. The wonders are immediate and accessible. Look up at the night sky tonight if you can. Really look at it. Those points of light are nuclear furnaces burning millions of miles away. That faint band of light is the disk of our own galaxy seen from the inside. Those dark patches between the stars are not empty, but filled with gas and dust that will someday form new stars and planets. Everything you see is part of a cosmic story that stretches back nearly 14 billion years and will continue for trillions more. You are part of that story. Your atoms were forged in stars. Your existence is a consequence of cosmic evolution. Every breath you take contains atoms that have been part of countless other structures over billions of years, atoms that will go on to be part of other things long after you are gone. You are a temporary pattern in the flow of matter and energy, a brief eddy in the cosmic stream. But you are real, and you are here, and you can look up and wonder. The universe is stranger than we imagine. The most terrifying things in space are real, and they remind us how fragile and improbable our existence truly is. But terror is not the only appropriate response. Awe is appropriate. Gratitude is appropriate. Curiosity is appropriate. The drive to understand, to explore, to push back the boundaries of the unknown, this is perhaps the most appropriate response of all. We are small, but we are not nothing. We are brief, but we are not meaningless. We are surrounded by dangers we cannot control, but we are also surrounded by wonders beyond counting. The terrifying things in space do not negate the beauty of existence. They intensify it. They make every moment more precious, every discovery more valuable, every connection between conscious beings more important. So do not turn away from the darkness, look into it, study it, learn from it. The universe has no obligation to be kind or safe or comprehensible, but we have the ability to face it with clear eyes and curious minds. We have the capacity to understand at least some of what is going on out there in the cosmic wilderness, and we have the privilege, rare and fleeting as it may be, of being part of the story. Before we truly conclude, there are a few more cosmic mysteries worth exploring, phenomena that add depth to our understanding of how strange the universe really is. Consider the problem of stellar mass black holes that are larger than they should be. When massive stars collapse, theory predicted that the resulting black holes should fall within a certain mass range. But gravitational wave detectors have found black hole mergers involving objects that seem too heavy to have formed from ordinary stellar evolution. Where did these overweight black holes come from? Perhaps they grew by merging with other black holes over billions of years. Perhaps they formed directly from massive gas clouds without ever becoming stars. Perhaps our understanding of stellar physics needs revision. Every answer leads to new questions. Every discovery reveals new depths of ignorance. This is the nature of science and the nature of the cosmos. We will never run out of mysteries to solve because the universe is inexhaustible in its complexity. Then there is the question of primordial black holes. These would be black holes that form not from collapsing stars, but from density fluctuations in the very early universe. In the first fraction of a second after the Big Bang, before atoms existed, regions of extreme density could have collapsed directly into black holes of various sizes. Some might be microscopic, smaller than atoms. Others might be enormous, potentially the seeds of the supermassive black holes we see at galactic centers today. Primordial black holes have been proposed as candidates for dark matter. If the universe is filled with black holes too small and too cold to emit detectable radiation, they would explain the gravitational effects we attribute to dark matter without requiring any new types of particles. The idea is appealing in its simplicity, but the evidence remains inconclusive. Searches for the gravitational effects of primordial black holes have found nothing definitive. Let us also consider the edge of the observable universe and what lies beyond. The cosmic horizon is not a physical boundary, but rather a limit on how far light has traveled since the Big Bang. There is presumably more universe beyond that horizon, regions that look much like our own, filled with galaxies and stars and perhaps life. But we will never see those regions because light from there has not had time to reach us, and thanks to the accelerating expansion driven by dark energy, never will. The true extent of reality might be vastly larger than what we can observe. Our visible universe might be a tiny bubble in an ocean of space that extends far beyond our ability to detect. Or the universe might be finite but unbounded, curving back on itself like the surface of a sphere. with no edge but also no infinite extent. We do not know which possibility is correct, and we may never know. There is something both humbling and liberating about these limits on our knowledge. We cannot know everything. Some questions may be forever beyond our reach. But this does not diminish the value of what we can learn. Every step toward understanding, no matter how small, is a triumph. Every mystery we solve opens up new mysteries to explore. The journey matters as much as the destination. The cosmic mysteries also raise philosophical questions about the nature of knowledge itself. How can finite minds comprehend an infinite universe? How can creatures made of atoms understand the quantum realm where atoms behave so strangely? Our cognitive abilities evolved to help us survive on the African savanna, not to contemplate cosmic horizons or black hole singularities. And yet somehow we can do it, imperfectly, incompletely, but genuinely. And we are not done. The tools we are building now, the space telescopes and gravitational wave detectors and particle accelerators, will reveal things we cannot yet imagine. The questions future generations will ask have not been formulated yet. The answers they will find will reshape our understanding in ways we cannot predict. We are at the beginning of the cosmic journey, not the end. The terrifying things in space remind us that we are not in control. We cannot stop a gamma-ray burst or prevent vacuum decay or halt the expansion of the universe. But we are not entirely helpless either. We can understand, we can prepare where preparation is possible, we can appreciate what we have while we have it. And we can share our knowledge with others, ensuring that what we learn does not die with us. This transmission of knowledge across generations is perhaps humanity's greatest achievement. Every child who learns about black holes or neutron stars or the Big Bang is connecting to a chain of understanding that stretches back thousands of years. Every teacher who sparks curiosity about the cosmos is planting seeds that may grow into discoveries not yet made. The light of knowledge passes from mind to mind, growing brighter with each generation. The universe may be stranger than we imagine. It may harbor terrors beyond our comprehension. But it also contains us, beings capable of imagining and comprehending. In the vastness of cosmic time, this may be a brief and fragile candle. But while it burns, it illuminates everything. If you have found this journey through the strange and terrifying cosmos interesting, please consider subscribing to this channel for more explorations of the universe we call home. Hit that like button if you enjoyed the video, and leave a comment sharing your thoughts about what terrifies or inspires you most about space. Thank you for watching. Keep looking up at the stars, and remember, the universe is strange, but you are stranger still, a collection of atoms that can ask questions about where atoms come from. That is something worth celebrating, even in the face of cosmic terror.